Okay, so we again start a new lecture. So that is lecture number 7 in phase equilibria. So just do a recap of last lecture. Now the recap of last lecture, in that lecture we worked out what is the change in the entropy, which was basically configuration entropy change, and that worked out to be your delta S worked out to be minus of R XA ln XA plus XB ln XB, and from this we determined what is delta G. This was for ideal solution, for which delta H of mixing was 0. As a result, we just made it delta T, delta S mix, and this was RT XA ln XA plus XB ln XB. So when we plotted this, when you plot this delta G of mixing as a function of mole fraction of B, so delta G of mixing goes like that. Okay, so this is what is delta G of mixing, and of course as you increase the temperature it goes further down. So this is at T1, this is at T2, where T2 is greater than T1. This is delta G mixing here. If you plot the free energy, so the free energy went like this. So this was GA, this was GB, and this was the mixing term delta G mix, and that is when you went from A as a function of XB. Of course, so this delta G mixing being negative, you can see that it will be negative because XA is less than 1 and XB is also less than 1. So ln of XA and ln of XB will be minus. As a result, delta G mixing will be negative. This tells you, this is basically the driving force for making a stable solid solution when two elements are mixed into each other. So now what we do is that we look at some other aspects of phase formation, and moving away from ideality is important. So first in this aspect we will, because ideal solid solution which say that delta H of mixing is no longer valid in case of in most cases because of atomic interactions and different bonds and so on and so forth. So we will have to move into regular solutions. Before we do that, we first discuss another important aspect of thermodynamics, that is chemical potential. Now basically chemical potential is a measure of how free energy G will change when the composition of the system is changed. And if we talk in terms of a phase, when the composition of the phase changes. All right. Now this requires us to assume to begin with that other thermodynamic parameters such as temperature, pressure are constant. So basically we are looking at the changes in the incremental changes in the free energy when you make very small changes to the composition of a given phase at constant temperature and pressure. So essentially what we do is that, let's say you have a phase and you add a few atoms of, if it consists of AB, okay, a few atoms of A whose amount is, so basically the amount is very small, let's say DNA. This is the incremental change to, so number of A atoms present originally in A phase are much larger than the amount. So this is the incremental amount, let us say incremental amount. So number of atoms which are originally present in phase A are much larger than this incremental amount, that is DNA. So as a result, we increase the size of the system by same amount, that is DNA, and this also leads to changes in the free energy. So free energy change correspondingly, let's say, is another quantity called as dg prime. So if DNA is very small, then dg prime can be expressed as a quantity mu A multiplied by DNA, and at this point temperature, pressure and Nb, which is the number of B atoms, they remain constant. So now here this proportionality factor mu A is called as chemical potential. So basically this is chemical potential of A in the phase which consists of both A and B, or alternatively it is also called as partial molar free energy of A in the phase. So this mu A is generally, mu A is, as we can see, is dependent upon composition. So you can represent this mu A as del G prime by del Na at constant temperature, constant pressure and constant Nb. So basically we are making this DNA so small so that there is no appreciable change in the overall composition of the phase. It is a very minute change, and this minute change gives rise to changes in the free energy. So incremental changes in the free energy upon incremental changes in the composition are represented by a quantity called as chemical potential. So this is chemical potential of element A in the phase. So now, so you can have, you can extend this approach to other elements also. So for a binary solution, let's say it's AB binary solution. So at, again, if temperature and pressure are constant, then we can say dg prime is equal to mu A DNA. So you are making changes in both A and B, D and B. So this is the quantity which is corresponding to changes made in A, and this is the chemical potential of B corresponding to the changes that are made in B. So if you change the pressure and temperature also, then free energy will be dg prime will be equal to V dP minus S dt plus mu A dNA plus mu B dNB. So this is about like a generalized equation of free energy change in a system. So you can extend this approach to a multi-component system. So for a multi-component system, this dg prime will be equal to V dP minus S dt plus mu A dNA plus mu B dNB plus mu C dNC and so on and so forth, or in a general form you can write this as V dP minus S dt plus sigma I mu I d Ni. So this would be the general form of changes in the free energy when changes in the various variables are made. So not all of them are made simultaneously. So when you, for example, change compositions, these are generally kept as constant. So as a result, you only worry about the changes in the composition. So this is a generalized free energy equation for incremental changes in the composition, correlating the chemical potential with the changes in the composition. So now let us now come back to binary phase. So we have a binary system. Okay. In this system, you have a phase which consists of XA moles of A and XB moles of B, as we started earlier. So XA, basically XA is nothing but mole fraction. So I would say it's not mole, it's rather mole fraction. Such that XA plus XB is equal to 1. So since we know the ratio of A and B, so what is A is to B ratio? It's nothing but XA divided by XB. Okay. So since ratio of A is to B is known in terms of XA is to XB, you can increase the size of the system appropriately so that the ratio of XA is to XB doesn't change. So what you can do is that, so this I wrote as 1 mole. So let's say you take 2 moles, so this will become 2 XA and 2 XB. So on and so you can write this as 1.1 XA and 1.1 XB. This will become 1.1. So you correspondingly increase the size of the system without changing the corresponding without changing the ratio of 2 elements. So as a result, what we can write is that dNA divided by dNB is maintained in such a fashion so that it's always equal to XA divided by XB. So let's say for an example, if XA is equal to 0.75, XB is equal to 0.25, then dNA by dNB will be 0.75 to 0.25. This is nothing but 3:1. So when you make a change in dNA and dNB, if it is in this ratio of 3:1, so you add 1 atom of N, 1 atom of B and 3 of A, or 2 of B and 6 of A, then this ratio is always maintained. As a result, the overall fraction of A and B in the system doesn't change. So overall composition is maintained without altering. So what you do in this situation is, if you maintain this ratio, then mu A and mu B, which are function of composition, do not change. All right. So now let us calculate what is the molar free energy. The molar free energy can be written in this case as XA mu A plus XB mu B, and this is equal to XA into dg prime by del NA plus XB into del G prime by del B. So this is the, so I can write in this slide, G is equal to XA del G prime by del NA plus XB to del G prime by del B. So when you now plot this, A, this is B. So you go as x, so you increase the mole fraction of B in the right direction, and on this y axis we plot molar free energy, okay. And what we have here is basically a situation like this. So the tangent, we can see that since it's a tangent to this, let's say this is the composition XB that we are interested in, XB. So the tangent will determine the chemical potential on two sides. This is mu, this is the free energy GA, GB, and what is this? That is what we will determine. So let's see what are these. So we know that XA plus XB is equal to 1. So we can write dXA is equal to minus of dXB, and we are writing G as mu A, XA mu A plus XB mu B, and we can write this as XA GA plus XB GB plus RT XA ln XA plus RT So this is what we did earlier when we calculated the mixing part. So let's say, so this is first expression. So this is what is the relation with respect to chemical potential. This is what is the relation as we obtained from mixing when we calculate the delta G mix. So basically it's XAGA plus XPGB plus RT ln. So XA ln XA plus RT XB ln XB. Now you equate these two equations. If you equate these two equations, what you get is mu A is equal to GA plus RT ln XA, and mu B is equal to GB plus RT ln XB. And you can see that these both of these terms, this and that, both of these will be negative, because XB and XA, as XA and XB are less than 1. So if you go to previous plot, what is this difference going to be? This is going to be minus of RT ln XA. And what is this going to be? This is going to be minus of RT ln XB. So basically these are two expressions you can represent. So you can see in this plot that when you make when you have a free energy curve, so of course you have free energy mixing for a given composition, the slope and its intercept. So you draw a tangent for a given composition, and the intercept of this tangent with respect to x and y axis will give you the chemical potential. So this is chemical potential, and chemical potential is related to the free energy of that particular element. It's the chemical potential is always chemical potential of element in a phase. So chemical potential of A or chemical potential of B, and this is the phase, this is the free energy plot for a given phase. So if you have different phase, you will have to draw a different curve for different phase. So if you have, for example, another phase, let's say that another phase has a free energy curve something like that, okay, then you will have to draw the tangent for that. So something like that you will have to do that. So anyway, this is for phase 2, this is for phase 1. So for a given phase, you can draw the tangent at the minimum, and the intercept of tangent with respect to x and y axis, that is A and B axis, will give you the chemical potential, and this chemical potential is related to the free energy of that molar free energy of element A by magnitude called as by magnitude minus RT ln XA. In this case of element B, it would be minus RT ln XB. So this is what is the chemical potential concept. As we have seen, chemical potential is nothing but, let's just redefine. So, chemical potential is essentially it describes minute changes in the free energy when you vary the composition of a particular, when you change the amount of that particular element in a given phase. So, basically it is the partial molar free energy of A in a phase. Okay. Similarly, you can have the same thing for B. So, you are specifying the property of a particular element in a given phase. So, from this we can determine what is the overall change in the free energy when you vary composition composition of all the elements. In the context of binary systems, the molar free energy can be sum of the partial molar free energies, which is mu A, the partial molar free energy of A multiplied by the fraction of A plus partial molar free energy of B multiplied by fraction of B, and this can be equated with the overall free energy equation to give you the magnitude of mu A and mu B. So, chemical potential of A in a phase is related to the molar free energy of A plus RT ln XA, and chemical potential of B is equal to molar free energy of B in that phase plus RT ln XB. So, this is what the concept of chemical potential is, and this is a very important concept, as we will see later on when we build up more about the phase diagrams, when we try to understand the phase diagrams and their formation for especially for binary solutions. Now, from ideal solution, let us move on to what we call as regular solutions. Now, why do we want to study regular solutions is that because we said that for ideal solution delta H mixing was equal to 0. Now, what does this mean? What did this mean? Well, this meant that in the solid solution of AB, there was no preference for AB bonds or AA bonds or BB bonds, because the bond energies of all these three bonds were equal. So, if you have AB solid solution will, if it is a random solid solution, you will have AB bonds, you will have AA bonds, and you will have BB bonds. So, correspondingly you will have bond energy EAB, you will have bond energy EAA, and you will have bond energy EBB. So, delta H mixing is 0 because there is no change in the internal energy, and that is because there was first of all there was no volume change, molar volume change, and there was no preference for particular type of bond. So, which means probability of having AB bond is same as probability of having AA bond, which is same as probability of having BB bond. What it meant was basically EAB was equal to EAA is equal to EBB. So, all three bond energies are equal to each other. As a result, there is complete randomization, and also there were no other electronic and structural changes which may happen because of different, say for different atomic sizes, there could be minute difference in electronegativities, there could be difference in electronic configurations, etc. So, there were no, so it was ideal to, you put two atoms, they just randomly mix into each other, sizes are equal, structure is same, electronegativities are same. So, there is no change in the internal energy of the system. But life is far from easier. So, in reality this does not happen. So, in reality what we have is delta H mixing in reality, for most cases delta H mixing is not equal to 0, it is either greater than 0 or less than 0. So, delta H mixing, so when you have delta H mixing greater than 0, the process of making the solid solution undergoes a reaction which is endothermic, which means heat is absorbed. if it's less than 0, then we call it exothermic, which means heat is evolved. So, that is the reality of things, and in this context, when we take a formalism, when we build a formalism about it, we take an approach called as quasi-chemical approach. So, what do we do in this quasi approach? First thing is EAB is not equal to EAA is not equal to EBB, and that is because they are different atoms. So, when they are different atoms, the bond energy of A, bond energy of B and bond energy of AB are not same as each other. However, for the sake of simplicity, we take Vm of A to be equal to Vm of B, which is equal to Vm of AB. We do not take any change in the, no change in molar volume after mixing. Okay. And there are other things like, there is no change in structure. You can say lattice distortion. No change in the structure by mean that it has if both of them were cubic, it remains cubic. I mean, but there could be subtle variations within the cubic system itself. So, or you can have distortion in the electronic structure. Etc., etc. So, basically we are taking again a slightly non-idealized situation, that is, these three are different, the bond energies are different, other than that it is still fairly ideal. And another thing is that bond energy and lattice parameter are independent of composition. So, all we have made a difference with respect to regular ideal solution is that we have taken the bond energies to be different for AA, AB and BB bonds. So, having assumed this, we will now move forward to determine the free energy of a regular solution vis-a-vis the changes in the free energy of mixing. So, we will stop here in this lecture. We will develop this approach in the next lecture and try to understand what is its implication in terms of free energy. So, thank you.